We're working on the second problem from two pulleys. So here we have a pulley system. This pulley is movable up and down. This pulley is fixed to the ceiling. What we know is that M1 is accelerating downward with an acceleration A, and we want to know the acceleration now of block M2. So think about what would happen if this block moved downward 10 centimeters, or I don't know, call it D. Right? So that means that 10 centimeters of string has to go from one side of the pulley over to the other. Where's that 10 centimeters of string going to come from? Well, half of it's going to come from this side and half of it's going to come from that side. So this is going to move upward, which is something we want to know. But it's going to move upward half as much as the other. So that acceleration would be A over 2. I'm just thinking about the string. So 10 centimeters of string comes over the pulley, 5 centimeters of that came from each side, which means that any distance this moves, that one moves half as much. Therefore, the velocity is half as much. Therefore, the acceleration is half as much. So just by looking at this setup, you can figure that out. You don't need to do anything else. Okay, we're talking about we're given the tension in the long snaky rope, and we're looking for the tension in this little tiny rope. And this is a case where you want to think back to why the tension throughout the rope is the same anyway, and part of it is because the rope itself is massless. And here, the pulley is also massless. The idea is that you can't have unbalanced forces on something that has no mass, because then the acceleration would be infinite, right? The acceleration is F net over m. And if m is really, really small, F net of any size will give you a very, very big acceleration. If m is 0, F net of any size will give you an infinite acceleration. So the tension being the same throughout the rope is partly about the rope itself being massless. If you think of a little piece of mass in the rope, tension left and tension right, if those are unequal, then that little piece of rope, which has basically 0 mass, would accelerate at an infinite rate. Okay, with that understanding, since we know the pulley is massless, if we draw an FBD for the pulley, it has this T2, which is in this rope, down, and it has 2 T's up. I know the forces on it have to be balanced because it's massless, so T2 is 2T. Okay, now we're getting to the question you probably thought you were going to solve for first, the acceleration of the acceleration of m1 in terms just of the masses in g. Okay, starting with FBDs. First for m1, it's accelerating downward, so I know the net force is downward. It has a weight, and T is pulling up. And then I want to also draw an FBD for M2 plus the pulley. The pulley is massless. It has 2 T's up. And then it has M2G down. This acceleration is up, by the way. So those will be bigger than this. Okay. So we want to pick our direction of positive wisely so that all the accelerations are positive, because when this one accelerates down, that one will accelerate up. Those are linked. So M1G minus T is M1A, and 2T minus M2G is M2A over 2, because we decided that that acceleration was equal to A over 2. And this is what's going to make our problem a lot easier, is that realization. That helps us out with the algebra quite a bit. I'm going to eliminate the t by solving m1g minus m1a, sub it in here. So 2m1g minus 2m1a minus m2g equals m2a over 2. Collect all my a terms on the right. 2m1 minus m2. G is left on the left. On the right, we have 2m1 plus m2 over 2 times a. So a will be 2m1 minus m2 g over 2m1 plus m2 over 2. Okay, so there's some algebra in there, so let's check first units. Yeah, this is mass divided by mass, so the units are going to be the same as the units of g, which are the units of acceleration. That's fine. Let's check special cases. What would happen if m2 were 0? This thing would be able to just fly up pretty easily. So if we make m2 0 here, 2m1 over 2m1, that's 1. Acceleration is g. Basically, this tension would be 0 without something on the pulley weighing it down. So this thing is just going to be in free fall. That's correct. What would happen if, let's say, m2 was equal to twice m1? So if I look in the denominator, if m2 is equal to 2m1, then this thing is actually going to balance out. So the t up on this one, holding up this mg, with 2t up here holding up 2mg, yes, those both should balance and we should get an acceleration of 0. So this thing works out in all the special cases.